Okay, let's just forget the science fiction movies for a second, all right? When we hear artificial intelligence, I know it's so easy for our minds to jump straight to, rogue Terminators bent on human destruction. But the reality we're actually living in right now, it's far more mind-bending and honestly a lot more fascinating. I mean, we are at a point where a journalist can sit down and have a completely fluent, totally interactive conversation with a computer program, like Inflection AI's chatbot Pi. The machine can literally come alive, learn through narrative, and talk to you about whatever's on your mind. So how do we actually get here? And where is this all going?
Well, here's our roadmap for today's explainer. We're going to start with the AI awakening. Then we'll see how machines actually learn, explore supercharging medicine and science, tackle the real dangers ahead, and finally, ground this whole AI revolution.
So, Section 1, the AI awakening. Because to really understand where we are today, we have to recognize that human beings have been dreaming about creating non-human minds since antiquity.
It's absolutely fascinating to track this modern journey. Back in 1951, fresh off his World War II code-breaking brilliance, mathematician Alan Turing actually predicted we'd eventually program machines to answer questions so well we wouldn't be able to tell if we were talking to a human or a machine. Fast forward a few years to 1956, and the term artificial intelligence was officially coined at Dartmouth College. For decades, the tech just kinda couldn't match the dream, right? Until 1997, when IBM's Deep Blue defeated world chess champion Garry Kasparov. And of course, that steady climb absolutely exploded in 2022 when ChatGPT became this viral global sensation, cranking out essays and poems in literal seconds.
But to make that ChatGPT moment possible, computer science had to undergo a massive evolutionary shift. See, for a long time, we relied on rule-based AI, like Deep Blue. These were basically expert systems loaded with human-programmed logic. Sure, Deep Blue could search 200 million chess positions a second, which is wild, but it was brittle. It wasn't really strategizing like us. Today, we've shifted to neural networks, like the AlphaGo system that mastered the impossibly complex game of Go. These networks are actually inspired by the 80 billion neurons in the human brain. They don't just follow rigid rules. They take in massive streams of data, and they learn by finding patterns.
Which brings us to Section 2, how machines actually learn. Let's take a peek right under the hood to see exactly how these pattern-seeking machines function and grow.
Now, you probably heard the term large language model, or LLM. It sounds incredibly complex, but the foundational concept, it's surprisingly intuitive. Systems like ChatGPT aren't actually thinking the way you and I do. They're just software programs that have consumed massive amounts of publicly available text from the internet. We're talking books, articles, websites, the whole shebang. By recognizing patterns across billions of words, they simply make highly educated guesses at the very next word in a sentence. It's just an incredibly powerful form of prediction that results in dialogue that feels, well, uncannily human.
But how exactly do you teach an algorithm to predict things accurately? Well, training an AI is actually surprisingly similar to training a puppy or even teaching a toddler. It all comes down to repetitive reinforcement. When an artificial neural network plays a video game or guesses a word correctly, it gets a little digital treat. The connections that led to that success get strengthened. When it fails, no reward. Over time, those reinforced connections completely overruled the weaker ones. So through millions of repetitions, the machine essentially learns how to win.
And we can literally see this learning happening in the physical world. Take veteran journalist Miles O'Brien, an arm amputee who's been training a bionic prosthetic limb. When Miles just imagines moving his missing hand, he generates these very faint electrical signals in his remaining muscles. Using what's called a Bayesian classification model, the AI in his arm studies the patterns of those signals. Miles and the machine are basically learning together. The algorithm labels his unique muscle patterns and relies on statistical probability to translate them into a mechanical command, like opening or closing a robotic hand. It adapts and gets more robust with every single use.
So, what happens when we take these predictive learning models and scale them way up? This brings us to Section 3, supercharging medicine and science.
Let's look at a type of AI called a convolutional neural network, or CNN. Think of it as software using a bunch of virtual magnifying glasses to comb through an image, hunting for specific edges, shapes, or textures. It pieces them together, makes a guess about what it's looking at, and then uses a process called backpropagation to correct its errors for next time. Researchers at MIT and Mass General Hospital are actually using this to look at mammograms and lung CAT scans. Their models, named Myri and Sybil, can recognize invisible precursor lesions and correctly predict cancer diagnosis up to 5 years before a human eye can perceive a problem. I mean, that is a massive leap forward for preventative medicine.
Now, the crucial point here is this staggering number, 200 million.
That is the amount of protein structures a deep learning model called AlphaFold successfully predicted. Look, proteins dictate almost every single function in our bodies, and their 3D shape determines exactly how they interact. For a really long time, the shapes of millions of proteins were a total mystery. But DeepMind trained AlphaFold on known structures, and it used that knowledge to predict essentially all the proteins known to science. All of them.
And why this matters is beautifully captured by computational chemist Patrina Kamya with this quote. She compares using generative AI in drug design to using filters on Airbnb. If you know the exact shape of a disease-causing protein, you can just ask the AI to generate specific molecules that fit perfectly into it, acting like a customized lock to disable the disease. So instead of decades of grueling trial and error, AI filters down the best candidates in just 48 to 72 hours. This could make life-saving drugs far cheaper and way faster to develop.
But here's a massive contrast for you. While AlphaFold requires staggering amounts of computational power and huge data centers, consider this shockingly small number, 19. That is the exact number of liquid neurons driving a brand new experimental autonomous vehicle over at MIT.
This introduces us to liquid networks. See, today's massive AI models aren't really sustainable for everyday on-the-go devices. So researchers actually drew inspiration from a microscopic worm called C. elegans, which has a tiny but incredibly complex brain. By altering how digital neurons talk to each other, they built a network that is so highly efficient it can run entirely locally on edge devices. That means no massive cloud computing required. Just imagine self-driving cars that don't even need internet connectivity to navigate new roads, or mountaintop cameras in California running local AI to spot the smoke of a wildfire the literal second it starts.
But of course, moving at this breakneck speed brings immense unintended consequences. So let's head into Section 4, the real dangers ahead. To understand how deepfakes are made, you really need to understand the Generative Adversarial Network, or GAN. It's basically this dizzying student-teacher loop. You have a generator algorithm that splats down random pixels to try and draw, say, a cat. Then a second algorithm, the discriminator, compares that to millions of real cat photos and basically says, nope, try again. They volley back and forth in this brutal adversarial loop thousands of times until the generator finally serves up an image that is completely indistinguishable from reality. And now, things have escalated even further to diffusion models. These things vacuum up billions of captioned images from the web. The system intentionally corrupts those images with visual noise, going backwards 6 billion times until the image is pure static. By learning how to turn an image into nothing, the AI learns how to reverse engineer pure noise down to the pixel to create a brand new, stunningly realistic image from just a simple text prompt. The barrier to entry for manipulating reality has been completely lowered. Basically, anyone can do it now.
So, this forces us to ask a really vital question. If science fiction Terminators aren't real, what are the actual, immediate threats we face as a society today?
Well, the near-term dangers are incredibly tangible. We're looking at a world flooded with AI-created disinformation and deepfakes that create a house of mirrors where we just don't know what's real anymore. We risk supercharging bias and hate content, seeing massive job replacements, and even making it easier for bad actors to develop bioweapons. Plus, these neural networks are frustratingly opaque. Nobody really understands exactly how they reach their decisions, making them almost impossible to audit. And folks, the impacts are already here. Recently, a single fake AI-generated image of a bombing at the Pentagon temporarily wiped $500 billion off the stock market in minutes. No joke.
The concern is so high right now that in May of 2023, top AI thought leaders signed this chilling single-sentence statement. They literally equated the existential risk of AI with pandemics and nuclear war. It's a technology projected to have a $13 trillion economic impact by 2030, which means there's a massive, massive commercial incentive to race forward. The world is frankly scrambling to figure out how to put guardrails around a runaway train.
Okay, let's move to our final section, Section 5, Grounding the AI Revolution. Let's take a deep breath and ground all of this in present-day reality. Let's go back to Miles O'Brien's personal journey for a second. Yes, the Bayesian learning algorithm is brilliant, but out in the real world, it's far from a sci-fi Terminator. When Miles tried to use it to simply set up a camera in his studio, the mechanical hook continually opened unpromptedly, just dropping things on the floor. It was a lot less robot takeover and more just, incredibly frustrating.
And honestly, that frustrating moment is a perfect snapshot of where we actually are right now. The choke point isn't that AI is too smart or malevolent. The choke point is how we humans communicate our intentions to it. Whether it's a prosthetic arm struggling to read skin electrodes or an autonomous car getting confused at an intersection, we are not at the robot takeover phase. We are simply in a frustrating, miraculous, and deeply collaborative learning phase with these machines.
Which leaves us with this final thought to carry forward. We are walking down a road to an entirely unknown revolution. We're teaching algorithms to mimic our voices, spot our diseases, and drive our cars, and in turn, they're completely reshaping how we work, trust, and live. So as we stand at the threshold of this new era, how will we choose to train the machines that are ultimately training us?